A ship weighing 50,000 tons is being pushed by hurricane-force winds toward rocks. One thing stands between it and disaster: a piece of metal you can barely see from the surface. So how does an anchor the size of a small car hold a vessel that weighs as much as 25,000 elephants? Spoiler alert, it's not about weight. It's something way cooler. Let's drop in. The big anchoring misconception. Okay, so everyone thinks anchors work like this. You throw a heavy rock in the water, it sinks to the bottom, and boom, your ship is magically glued in place. Simple, right? But if that were true, we could just use giant concrete blocks, or a bag of anvils from a cartoon, or honestly, just really committed optimism. Yet somehow, ships use these elaborate metal contraptions with specific shapes, calculated angles, and entire chains attached. There's a reason for that, and it's going to blow your mind. Here's the truth. An anchor isn't really about weight. It's about grip. It's about something engineers lovingly call holding power. And the secret ingredient is the same thing that makes your shoes work: friction. Think about it. If you're wearing slippery socks on a hardwood floor and someone pushes you, you're sliding all over the place. But if you're wearing sneakers with good grip, you stay put. Anchors are basically the sneakers of the maritime world, except they're made of steel and weigh several tons. Fashion forward? Debatable. Effective? Absolutely. From rocks to rocket science. Let's rewind a few thousand years. Ancient sailors didn't have fancy engineered anchors. They had rocks, literally just big rocks tied to ropes. And you know what? It kind of worked. Not great, but it worked. The ancient Greeks and Romans upgraded to stone anchors with holes drilled through them for ropes. Then someone, probably after losing their stone anchor for the 100th time, had a brilliant idea. What if we made it out of metal and gave it pointy bits that dig in? Enter the stock anchor, which dominated maritime engineering for literally centuries. It had a long shank, a crossbar called a stock, and two flukes, those curved pointy arms. You'd drop it overboard, the flukes would hit the seafloor at an angle, and as the ship pulled on it, those flukes would dig in like a fork in mashed potatoes. Revolutionary. The stock anchor was so effective that it remained basically unchanged for over 2,000 years. That's longer than most technology sticks around. We went from flip phones to smartphones in like 15 years. But the stock anchor? Nah, we're good for 2 millennia. But then the Industrial Revolution happened, ships got bigger, and engineers started asking, can we do better? And oh boy, did they. Modern anchor types, a lineup of champions. The plow anchor, the CQR anchor. First up, we've got the plow anchor, which looks exactly like what a farmer uses, except underwater and made of steel. Invented in the 1930s, this thing was a game changer. It has a single pivoting fluke that digs into the seafloor and literally plows through it as the ship pulls. What makes it brilliant is that it self-rights. No matter how it lands, it rotates into the correct position and digs in. It's like a cat. It always lands on its feet, or in this case, always lands on its fluke. The plow anchor works great in sand, mud, and grass. Yes, underwater grass is a thing, and yes, anchors care about it. The Danforth anchor. Next, the Danforth. This one looks like a giant wishbone with 2 flat triangular flukes that fold up for storage. When it hits the seafloor, those flukes pivot outward and dig in at a shallow angle, creating a massive holding power. The Danforth is especially popular with smaller boats and yachts because it's lightweight but punches way above its weight class in terms of holding power. A 20-pound Danforth can hold a boat in conditions where you need a 50-pound traditional anchor. That's the maritime equivalent of getting 3 for 1 at a sail, except your life depends on it. The Meerschaum anchor. And then there's the mushroom anchor, which is exactly what it sounds like, a giant mushroom made of metal. You drop it into soft mud, and it sinks down and creates suction. The mud fills in around the cap, and suddenly, you've got nature itself holding your anchor in place. Meerschaum anchors are used for permanent moorings, buoys, platforms, things that aren't moving. They're the couch potatoes of the anchor world. Drop them once and they're staying there forever. Or at least until someone really needs to dig them out, which is a whole nightmare scenario we won't get into. The Bruce or claw anchor. There's also the Bruce anchor, which looks like a three-pronged claw. Invented in the 1970s for oil rigs, this thing is a beast. It works across multiple seafloor types, sets quickly, and has excellent holding power. It's the Swiss Army knife of anchors, versatile, reliable, and kind of looks like it could fight crime. The physics. Why it actually works. All right, let's talk science. Buckle up, because this is where it gets really cool. When an anchor hits the seafloor, several forces come into play. You've got the weight of the anchor pulling down, that's gravity doing its thing, but more importantly, you've got the horizontal pull from the ship trying to drag the anchor across the seafloor. That horizontal pull, that's what makes the anchor dig in. The flukes, those pointy parts, bite into the seafloor material. As the ship pulls, the flukes dig deeper, creating friction and resistance. The harder the ship pulls, the deeper the anchor digs. It's a beautiful, self-reinforcing loop. Now, here's the magical part. An anchor can generate holding power that's 8 to 20 times its own weight. Some specialized anchors, even more. A 10-ton anchor might provide 150 tons of holding force. That's not magic. That's physics, baby. The formula involves something called the coefficient of friction between the anchor and the seafloor, the surface area of the flukes, and the angle of pull. Engineers have spent decades optimizing these variables to maximize grip. The chain effect, the unsung hero. But wait, there's more. The anchor isn't working alone. That chain attached to it, that's not just for show. The chain is doing half the work, and nobody talks about it enough. When you drop an anchor, you don't just drop it straight down. You let out a bunch of chain, usually 3 to 7 times the depth of the water. So if you're anchoring in 10 meters of water, you might let out 50 meters of chain. Why? Because the chain creates a curve called a catenary. The weight of the chain causes it to sag, and that sag means the pull on the anchor is almost entirely horizontal, not vertical. Horizontal pull makes the anchor dig in, vertical pull just yanks it out of the seafloor. The chain also acts as a shock absorber. When waves rock the ship, the chain stretches and adjusts, smoothing out sudden jerks that might break the anchor loose. It's like having suspension on a car. It makes the ride and the anchoring way smoother. And here's a fun fact. The chain itself provides holding power through friction against the seafloor. In some cases, especially in lighter conditions, the chain alone can hold the ship without the anchor even needing to dig in much. The anchor and chain are basically a tag team, and they're both pulling their weight, literally. The seafloor. It's all about location. Location, location. Now, let's talk about what the anchor is actually grabbing onto, because not all seafloors are equal. Sandy bottoms, excellent for anchoring. Sand provides great friction, and most anchors dig in beautifully. It's like the Goldilocks zone of seafloors. Not too hard, not too soft, just right. Mud. Also great, especially for mushroom anchors and plow anchors. They sink in and create suction. The softer the mud, the deeper they go, and the better the hold. Rocky bottoms. Tricky. Modern anchors like the Bruce can wedge into crevices, but if the bottom is smooth rock, you're kind of screwed. The anchor just slides around like it's ice skating. Not ideal. Grass and weeds. Underwater vegetation can actually help. The roots create a tangled mess that anchors can grip. It's like anchoring in nature's own rope. Coral. Do not anchor in coral. It's environmentally terrible, and also coral doesn't provide good holding. It's brittle, it breaks, and you'll destroy a reef while your anchor fails anyway. Lose-lose situation. Modern ships use sonar and seafloor surveys to figure out what they're anchoring into. There are entire databases of seafloor composition in harbors and anchorages. Because when you're parking $1 billion cargo ship, you really want to know if the bottom is sand or slime. Modern anchoring systems. High-tech parking. Today's big ships have anchoring systems that would make ancient sailors weep with envy. We're talking massive windlasses. Those are the machines that lower and raise the anchor, powered by hydraulic or electric motors. Some can handle chains weighing hundreds of tons. Modern ships also use dynamic positioning systems, computers and GPS that control the ship's engines and thrusters to hold position without even dropping an anchor. It's like hovering, but for ships. These systems are used on oil rigs, research vessels, and any situation where traditional anchoring isn't feasible. But even with all this fancy technology, traditional anchors are still essential. They're the backup when GPS fails, the emergency brake when engines die, and the reliable old friend you can count on when everything else goes wrong.
So what happens when an anchor doesn't work? Sometimes the ship drags anchor. The anchor breaks free and slides across the seafloor while the ship drifts. This usually happens in storms when the wind and waves are too strong or when the anchor didn't set properly in the first place. You're basically watching your ship slowly slide toward disaster, and there's not much you can do except drop more chain, deploy a second anchor, or start the engines and get the hell out. Other times, the chain breaks. Chains are incredibly strong, but they are not indestructible. Corrosion, wear, and sudden shocks can cause links to snap. When a chain breaks, the anchor is gone forever, sitting on the seafloor like a very expensive paperweight. Ships carry spare anchors for exactly this reason. Then there are the truly embarrassing failures, like the time someone forgot to attach the anchor to the chain and just dropped an anchor into the ocean. Gone. Or when an anchor gets tangled in underwater cables, pipelines, or, awkwardly, someone else's anchor chain. One of the most famous anchor failures was the SS Edmund Fitzgerald, which lost its anchors in a storm on Lake Superior in 1975. The ship eventually sank, and while the anchor failure wasn't the main cause, it certainly didn't help. Anchors failing during storms is basically every captain's nightmare. So there you have it. Anchors are way more than just heavy chunks of metal. They're sophisticated friction machines, carefully engineered to grip the seafloor and hold ships weighing thousands of tons against nature's fury. They've evolved over thousands of years from literal rocks to high-tech marvels with optimized fluke angles, self-righting mechanisms, and holding power ratios that would make a physics teacher smile. Next time you see a ship peacefully sitting in a harbor, just remember, somewhere beneath the surface, there's an anchor dug into the seafloor, a chain creating the perfect catenary curve, and friction doing all the heavy lifting. It's basically the maritime version of speak softly and carry a big stick, except the stick is made of steel, weighs 10 tons, and is currently buried in sand. If you enjoyed this deep dive into maritime engineering, consider subscribing for more content about the clever solutions that keep our world functioning. No pressure, but also there's literally tons of pressure happening on that anchor chain right now, so maybe think about it. Thanks for watching, and remember, always check your anchor before a storm, and maybe make sure it's actually attached to your ship. That's important. See you in the next one.